again, a very peaceful, relaxing, long afterlife. So that leaves us then with the high mass stars, the ones that weigh several times the mass of our sun or more at birth. And in particular, stars that weigh at least 8 times the mass of our sun, they can go through a lot of different stages of fusion over the course of their life. And it turns out the more massive a star is, the faster everything happens, the faster it evolves. So if you have a 25 solar mass star, so that's a really massive star, and there aren't very many that weigh that much when they're born, it'll only spend about 7 million years burning hydrogen in its core. And then less than 1 million years burning helium. And then 600 years burning carbon. And at that point it's at 600 million Kelvin in the center. And then maybe 1 year burning neon in the core. And then 6 months burning oxygen. And then 1 day burning silicon. And when the star burns silicon, it produces iron. And it turns out you can't take an iron nucleus and any other nucleus and merge them together and get energy out. To merge an iron nucleus with any other nucleus in a fusion process, you have to put in extra energy. So once you burn silicon, you end up with a core that's primarily iron, and you can no longer do any fusion in the core. Now what you can do is build up an iron core and then have fusion going on of these other elements in shells surrounding the core of the star. And that'll work for a while to sustain the star. But eventually that iron core is going to get so big, so massive, that its own gravity, just of the core alone, is too much for it to sustain itself. And you get a gravitational collapse of that core. And so this is what that looks like. This is actual video from a supernova somewhere in our galaxy that we received from some aliens. Thank you, NASA. So what happens when the burning ends? The core collapses. Okay, so when the core collapses, it happens very quickly. You're taking, essentially, the core of iron that collapses weighs about 1.5 times the mass of our sun. So this is a big object. And it goes through just a gravitational free fall inward at as fast as 1/4 of the speed of light. So it only takes about 1/4 of a second to collapse down. And what happens is, it collapses from Earth size. It's the mass of our sun or more compressed to the size of the Earth because it's just nuclear matter, right? Iron nuclei. And then it collapses down to something about 30 kilometers in radius. And at that point, it's just nuclear density or higher. It's a very solid object. And as more matter tries to fall in on top of it, it bounces off. And this is the part where we don't really understand what happens next. So we think that inner core becomes rigid because it's at nuclear density. We call it a proto-neutron star because it's largely made out of neutrons at that point. As outer layers of the core fall in, they bounce off, and that gives you an outgoing shock wave that heats whatever other matter is trying to fall in on top. The problem is that shock wave tends to stall out, and there are very detailed 3-dimensional supercomputer simulations that folks are trying to do to understand how do you explode a star. And it turns out really hard, and there's a lot of physics involved, and we're always pushing the limits of the computational power to include more physics and try to get this to work. So we don't completely understand how the star explodes, but obviously we see them happening in nature, so we know this works. And we just have to figure out the full answer. We think neutrinos actually play a major role in this process. There are an awful lot of neutrinos being released in all the nuclear physics processes going on in the core of the star. And we think a combination of neutrinos and convection, stirring, mixing of the material somehow managed to revive the shock wave and blow off the outer layers of the star, producing a supernova explosion. And if you have a 25 solar mass star, you manage to explode over 90% of its mass. And you leave behind maybe the last 10% as a compact object that's left behind. So this is kind of the part where for me, the stars really get interesting. The behavior after the supernova explosion. So one supernova that you're maybe familiar with is SN 1987A. So this is the before